Welcome back to the extension to Chapter 11. Yes, we are going beyond just the 6 sections. We're doing an extension. We will also be doing a supplement. But the extension is on normal distributions. We just got done looking at binomial distributions. Normal distributions are similar in that binomial distributions, when you have enough data, are normal, but they're nowhere near as complicated and they don't have complicated formulas. So let's look to see what we're going to be doing with this though. Our learning targets, I can recognize normally distributed data, and I can use the characteristics of normal distributions to solve problems. And so, a normal distribution, what it is, a normal distribution shape is what's called bell-shaped. The normal curve, the bell curve, are things that you may have heard about, and it looks like this. The very, very first slide has a normal curve in the background of the slide. And so it's bell-shaped, looks kind of like an old bell. Other things, the mean is at the center. This would be the mean of the distribution. X bar goes right there. Also, as you can probably see, it is symmetric about the mean. It's going to be the same on both sides. That's not just right here. That's normal distributions in general. And then it has a horizontal asymptote at y equals 0. It gets closer and closer and closer, but it'll never actually go across the axis. Now, what's really cool about a normal distribution is that if we take the probability of an interval, or an area underneath it, that's going to give us the probability of the interval. For instance, if we found the area between this x value and the mean, that would give us the probability that it would give us a probability of getting something in that interval. And we'll talk about that a little bit more later. And you might be thinking, all right, well, how am I going to find the area underneath this thing? Well, area under a curve like this would be a calculus topic, so we're not going to be finding that by hand. But even in calculus, even in statistics, we do not find the area using that because the equation for this graph is downright ugly. If you're wondering what it is, don't panic at this. You do not need to know the equation. It's not even in our book. But the equation is this. It's y equals 1 over the standard deviation times the square root of 2 pi times e to the negative 1/2 times x minus mu over sigma squared. Mu is the population mean, where x bar is the mean of the sample. We can just assume that they're basically the same right now. But yeah, that is ugly, and we don't use this equation. Some people figured out a lot of stuff about it earlier, and it's in tables, and we use those tables. So you can ignore you saw this. Don't let it haunt your dreams or anything like that. You won't have to use it. So how will we use a normal distribution? Well, when we have our normal distribution that we just had with the mean at the center, some cool things happen. If we go out one standard deviation each direction, and right now we just have the notation. We'll throw some numbers in here in a second. What we can tell about this one standard deviation over, first, it actually hits at the inflection point, which is where it goes from curving down and it starts to curve back up again. That's just a cool feature of it. More importantly, in between -1 and 1 standard deviation, we get 68% of the data, which if we really want to break it down, that means half of it being the symmetric, half 34%. So there's 34% right here, 34% right here. If we go out another standard deviation to 2 standard deviations away, we get 95% of our data is going to be in between those. And the 95% is in a box partly because this is a really common one that we're going to use, and we're going to use that in the supplement. And it's also partly in a box because apparently I accidentally clicked to outline the box and did not realize it until right now. But it actually works out because this 95% is going to be really big for what we're doing in the next couple days. And so within 2 standard deviations is 95%. Within 3 standard deviations of the mean, we get 99.7% of the data. And so if you're outside of 3 standard deviations, that 0.3%, that's what would be considered an outlier. And so we could find the percentages of each of these individual pieces. We know that this is 68%, and we know that this is 95%. And so to figure out what if we got in between the red and green lines, that would just be 95 minus 68. And then if we just wanted, what about in between this red and green line, in between 1 and 2 standard deviations, that would be the 95 minus 68 to get both of them, and then divide by 2 to get one of them. So what's the probability that it's going to be bigger than 3 standard deviations? Well, inside of 3 standard deviations is 99.7, which means outside is going to be 0.3%, which is split up into 2, so we'd have 0.15% on either side. And so we're going to figure these things out using just basic subtraction and then division by 2. And in fact, what you could do, you could actually figure out the percentages of each of these intervals, and then just add the ones together that you're interested in. When we do this, the mean will be a number and the standard deviation will be a number, and then we would get interval numbers. For instance, we could say that we're looking at test scores, and the mean was an 80%, and the standard deviation was 5. That means between 75 and 85, you'd have 68% of the data. The probability of getting between 75 and 85% would be 68%, or 0.68. The probability of getting above 2 standard deviations, which would be 80, 85, 90, probability of getting above 90% would be 1 minus 0.95. It's 5%. 95% is inside, 5% is outside, and then divide by 2 because we only want 1/2 of it, and so it would be 2.5% of getting above a 95%. And so that's the kind of thing that we're going to be doing with this. It is remarkably easy, and I think there's a total of 8 problems. With like 3 setups and you just answer a few questions. It takes a couple minutes. It is super easy. We don't get super in-depth in this right now. This is a big part of statistics, though. Anyway, before we end, this has a name, a rule name. It's a rule and it has a name. And you know how a lot of times in math, rules are named after people, or they're just named things that have absolutely no relationship to the rule at all? That's not the case here. This is called the 68, 95, 99.7 rule. The beautiful thing about that is on something like a test, if you have a problem like this, I will say find the probability using the 68, 95, 99.7 rule, which means you don't even need to remember what these percentages are because it'll be in the question. So that is the extension. I look forward to doing some problems with you on this in class, and I will see you then.